Good morning. A small announcement. You've noticed there is no coffee in this room, but there will be a coffee break. So if you follow me at the coffee break, I will show you where it is hidden. It's one floor down. Here it's the third floor. So let's say the second floor, but really you have to follow a passage. It's Corridoio della Direzione, so the director's corridor. Okay, let's start. Mr. Chen.
Okay, welcome to the Friday morning session. The first speaker is Diego Dominici. He's going to talk about generalized Hahn polynomials of type 1. Please.
Thank you. Well, you are kind of forced to come here for the last session of talks, but at least as a reward, you see this beautiful room that otherwise you may have no chance to see, so there is some compensation. I want to thank the organizers for putting together such a nice meeting and giving me the chance to be here. It has been a very rich and intense week, tons of discussions and interaction, many different topics. I think that every branch of mathematics more or less has been represented so far, from analysis to algebra, combinatorics, stochastic processes. So it has been, in a sense, like a very rich Italian dinner, right? And now we may feel a bit full. So for Monday, we have some antipasti with some of the talks. And then on Tuesday, some primi, some heavy pasta dish, perhaps. Wednesday was a condi, maybe some meat or some fish. Yesterday, dolci, no references to Nicholas in any way, just in general. And so, what can we do now, right? I mean, it has been plenty, and no, that even may be too much. So this is just a grappa, okay? So it's just a small, tiny talk to help you digest the rest. There may be not much into it, but I hope that you enjoy it and get something out of it. Okay, so the talk will be along the lines of one of the middle topics in the title of the meeting, so namely orthogonal polynomials. There have been other talks, so there will be a bit of repetition. I apologize for it, but I just want to introduce some notation from the beginning to the end of the talk, so if you get bored, you can just zoom out for that. We will talk about some special measures called semi-classical. Again, they appear in some of the talks, especially yesterday. And also about what happens when you have an extra parameter and then the toda lattice plays a role. I'm sure that all of you also know about that. And then when you put everything together. So I'm not going to use the classical setup of orthogonal polynomials in the sense of writing an integral and a measure. I'm going to use the notion of linear functionals. So L here will be a linear functional defined on the space of polynomials with complex coefficients. And phi will be a basis for the space of polynomials, which I will represent as an infinite column vector. And just for simplicity, I will ask the elements of the basis to be monic and of exact degree n for the n elements, so to avoid any permutations or any changes there. And then if you apply the functional to that basis, you get what are called the moments, in this case the generalized moments, in the sense that for most of the literature, the basis is chosen to mean the monomial basis, and so the functional applied to the monomials are the usually called moments. But of course, not any linear functional will give rise to a sequence of orthogonal polynomials. So the condition will be that the gram matrix associated with B should be non-singular. And if that's the case, then one can do a LDL decomposition. So one gets a matrix of coefficient C, which is lower triangular, and a diagonal matrix H, whose elements should be all different from 0. H will represent the norms, or the square norms of the polynomials, and C will be the coefficients representing the bases in terms of the polynomials, not the other way around. In the classical case where you have positive definite functionals, the elements of H will be strictly positive, but here in the quasi-definite case, it is enough that they are different from 0. They could be complex numbers, they could be anything you want, but not 0. And how do you do this decomposition? Well, it's very explicit, so there's an algorithm that one can use. There might be more efficient ones. This is just the basic one. And as I said before, this matrix C is not the matrix of coefficients of the polynomials, but the matrix representing the transition from the basis to the polynomial. So if you want to represent the polynomials, you have to take the inverse. And that's the part that can be computational very intense, or in some cases, even impossible at the moment. And the orthogonality condition then just takes this very simple form. Now, one can do C with the polynomials. For instance, one can consider the multiplication operator acting on the space of polynomials. I'm sure that you all know that gives rise to a three-diagonal matrix, which usually is called the Jacobi matrix, especially in the case of orthonormal polynomials when the matrix is symmetric. In this case, because we are working with monic polynomials, it's not, but it's still three-diagonal. And the three sort of main diagonals have elements 1 because of the monotonicity of the polynomials, beta I, and gamma I. So those are the terms in the three-term recurrence relation. Nothing new so far. And then because of the way that this linear functional acts on the polynomials, one can see connections between the norms and the coefficients gamma. And then if one will focus on the second leading coefficient, the one multiplying x to the n minus 1, sometimes in the literature people put the plus, I put the minus to preserve the signs. One will see that that one is related to the beta coefficients by this simple formula. So the norms go with the gammas, and this coefficient sigma with the betas. And before I introduce the idea of using just any basis, not necessarily the monomial basis, because for the discrete case, for other applications also, but for the discrete case, the monomial basis is very bad. It doesn't behave well with respect to shifts and actions of certain operators that one wants to use. So it's much better to use this basis of Pohammer polynomials or falling factorials, if you want, that can be defined this way in terms of the rising factorials. Unfortunately, notation across books and papers is wild. So that's why I stress that this with the index below is the Pohammer symbol or the raising factorial, not the other way around. And one important property that these Pohammer polynomials have is that they can be linearized, and this helps to construct the Gramian matrix in terms of that basis. Moreover, there are eigenvalues with respect to a differential operator. One has to take derivatives n times and then multiply by c, say, n times to leave things around. And so this will be used when we talk about the total lattice. So just to give you an example where things work, very easily. One of the classical families of discrete orthogonal polynomials are the Maxner polynomials. The linear functional is given in terms of one Pohammer on top, and then c to the x over x factorial. One can compute these generalized moments very easily. And then if one will use that linearization formula, one can compute the elements of the Gram matrix also in a very explicit way. And then, and of course the devil is always in the details, but it can be done. One can do an LDL decomposition to find explicitly the elements of that matrix C and H. And then if one do the inversion, which in this case is not too bad thanks to this binomial coefficient here, then one gets explicit representation for the Maxner polynomials in terms of the Pohammer basis. This is an extremely toy problem. I just presented as an example where things can be all explicitly computed. I mean, one of the main questions, at least I have, when one moves away from the classical families, is how to generate the polynomials. Because it's not just a matter of going to Matematica and inputting Charlier or Maxner or even the hypergeometric representation. Now there is nothing for them. And if one tries to use Gram-Schmidt, it runs into problems almost immediately. For one thing, most of the methods like Giorgi or Gram-Schmidt at some point try to take square roots, right? Because they try to orthonormalize the system. But again, these have non-positive entries in principle, and so you can run all sorts of problems there. And then Gram-Schmidt tried to orthogonalize with respect to the previous elements in the sequence, so you have to take inner products with respect to those elements, and those things in practice can be enormous. And the computer can either take forever or just stop working and tell you that that summation is unavailable. Yes, and also for the very complicated weights, the main problem is not the algorithm, but the summation needed to implement the algorithm. And so unless you have an extremely efficient summation package, the process just stops. At least in my experience. Maybe, of course, there are more powerful techniques. So one possibility is to use this so-called Chebyshev's algorithm or modify Chebyshev algorithm, which relates the moments and especially the inner products of the bases that you're working with the polynomials, with the coefficients of the three-term recurrence relation and that matrix C that we were looking at before. And it's a very efficient method to construct all the elements that you need for a given family of polynomials. So the idea is to consider a matrix of so-called modified moments where you take inner products between the elements of the bases, in our case would be the Pohammer bases, and the polynomials. And this has to be lower triangular, and the elements in the diagonal have to be precisely the norms. And then if you play around a bit with the multiplication operator and you let the matrix J explicitly appearing, you can get a very simple relation between, and I didn't say this, I am also assuming that the basis that I'm working with has a three-term recurrence relation. Or in other words, that the multiplication operator can be decomposed in a three-diagonal matrix. That is true for many bases, including the monomials. That's the original Chebyshev's algorithm, but can be also used in other bases. And so the idea is to get a connection between that simple three-diagonal matrix, which is explicit, and the matrix J that has the elements that you are trying to find. And this is the relation, just that you have multiplication on either side.
That is a combinatorial interpretation.
Is it?
Yes.
Okay. And if you extract the relevant elements in that equation, there are not too many because the matrices are 3-diagonal, you get formulas for the gamma elements and for the betas, and then an algorithmic way of constructing all the elements in the matrix. And so this is very efficient if you can compute these modified moments, which it can be done in the cases that I'm going to talk about. So again, just to fix the ideas for the Meixner case, the Pohammer polynomials satisfy this very simple three-term recurrence relation. So the last term with phi n minus 1 is not there, and the middle term is just n. And then using the Chebyshev algorithms, one can compute explicitly all the entries in C and H. The modified moments in this case also have a very simple structure, and from the Chebyshev algorithm, one will obtain the well-known three-term recurrence coefficients. In more complicated cases, one may not get explicit expressions, but at least we get like enough data using Matematica or Maple to be able to verify hypotheses on the coefficients, especially if one has these nonlinear recurrence relations connecting them, or nonlinear differential equations, et cetera, et cetera. And so at the very least, if it doesn't produce an explicit formula, it can give you enough raw data to then work with it. So what do we know about orthogonal polynomials? I mean, if I will take a sample asking which ones you know, I'm pretty sure that you will say Jacobi, Laguerre, Hermite. Then depending on your area of specialization, you may maybe add also some of the discrete ones, the more strange ones like Wilson and dual Hahn may not be something that you have worked with. But at least these are the ones that we know explicitly. We know all the elements associated with them, and it is typical to put them in this so-called ASCII scheme, where, okay, this is covering a bit, but this denotes the hypergeometric representation that they have. And the levels indicate that one can take limits to go down. And so in principle, starting from the Wilson polynomials, one could go anywhere. There is a similar one for basic or Q orthogonal polynomials. But the point is that if you will look at just like this, you'll say, this is great. There's a lot of order in there because of this limit structure. But it's misleading because you are mixing a lot of different animals in the same cage. What I'm trying to say. That what one has to really see is the operators acting on them. And so there are clearly defined families among those. One that respond to the derivative operator. Those are the classical polynomials of Jacobi, Laguerre, and Hermite. With respect to the difference operator, one would have the Hahn, Meixner, Krautchuk, and Charlier families. If one will consider now sort of shifts, but along the imaginary axis, out will come Wilson, continued Hahn, dual Hahn, and Meixner Polacek. And with respect to divided difference or quadratic lattices, Raka and dual Hahn. And so that sort of separates the families and tells you which method one should use to understand them. Once one has an operator, then one can start talking about this notion of semi-classical orthogonal polynomials. So how to continue those columns in the ASCII scheme upwards, but along the sort of column related to a given operator. Not so much in terms of hypergeometric representations because we don't have those. And so if we will have a linear operator that either preserves the degree or lowers the degree, but certainly doesn't increase it, so it's not the creator operator in the space of polynomials, then one will say that a family is semi-classical with respect to that operator if it satisfies this Pearson equation. So when L is taken a multiplication with respect to one of the two polynomials that will appear in the Pearson equation and the operator acting on Q, where Q is any polynomial, that gives you back L applied to the second polynomial times Q. And these are fixed polynomials that are associated with the given operator and the given functional. And one takes a look, there is a more complicated definition in general, but this is plenty for what we are going to do, at the degree of the difference of the polynomials, and that number S is called the class of the semiclassical family. Classical polynomials are those of class S equals 0. In particular, since we are going to talk about discrete orthogonal polynomials, one can take a look at the shift operator and at the class of linear functionals represented by sums or series rather than integrals. And in this case, the Pearson equation for the linear functional can be transformed into an equation for the weight function rho. And so one can then take that and play around trying to find all possible pairs, phi and psi, that will satisfy that equation for a given class. And so for the classical polynomials, one gets the known one, Charlier, Maxner, and Hahn. And then one could then decide to say, okay, what are the ones now on top? So the semiclassical polynomials of class 1. And we did that with Paco Marcechan back in 2014. And we obtained 5 canonical families. One that was already known in the literature and was called Charlier polynomials. Generalized Charlier polynomials. Even that the formula for the weight function was not consistent. Some people use just factorials here, but the idea was clear. People had also looked at the so-called generalized Maxner polynomials, where this will be the Pohammer symbol that one will already have in the Maxner polynomials, and now one will divide by another one. And then we got some that had not been around before, or at least we didn't see any references. And we call them generalized Krautschuk in the sense of being related to the Krautschuk polynomials. Generalized Hahn, very much with the same Hahn weight, but adding this c to the x, which is critical. And another type of generalized Hahn with argument 1, just with the same as the classical Hahn polynomials, but with a more complicated structure in the Pohammer symbols. And then besides those, there were also some polynomials related to the classical ones, an addition of Dirac masses at the end of the interval of orthogonality, but I will not mention those. And so the title of the talk is here, right? So these are the ones that I would like to say something about. Now, what is this Pearson equation? I mean, one has it at the level of functionals, which is nice, but I would like to extract some information from it. So if we go to the level of operators acting on vectors of polynomials and giving you a matrix representation for them, one can do some simple calculations to try to relate the matrix associated with the, say, shift operator and the Jacobi matrix. And when you do that, you get sort of a Pearson equation for the matrices M and J, involving also the polynomials, phi and psi, which contains all the information that you need to know about the return recurrence coefficients, only that this is now a purely algebraic way. In many cases, it's convenient to work with the orthonormal polynomials because then you see the h is gone and you just get the congruence relation. And you can say, okay, you have to solve for j and m, but you have only one equation. But of course, j and m have to satisfy some compatibility conditions in the form of a commutator. And so you get two equations. One that you can compute very much for any family, so you can do this and just store the connection between J and M. And one that will depend on the different families. And the solutions of that system are nothing else than the Lagarde-Freud equations. Okay, some people will say you get them of higher degree than you want, right? Because you have these high powers involving in the polynomials phi and j, but okay, you can then simplify as much as you want. But I will say that at least as a formula that one can write for any Lagarde-Freud equations, well, that's it. And so, again, just to see how it works at the simple level, you can do this for Meissner polynomials, and you get a trivial set of Lagarde-Freud equations in which the variables are completely decoupled, and it's extremely simple to solve explicitly for beta and gamma. And as a reward, so to speak, because you also find the elements of this matrix M associated with the shift operator, you can get also equations for the shift of a polynomial, both the forward and the backward shift. And if you will combine those, then you get difference equations for the polynomials. So it gives you all the structure you want, at least at the level of the variable x. We haven't introduced any new variable yet. If you introduce a new variable, as these polynomials all have, well, not all, but remember that most of the families have this c to the x term. In some, it's taken to be unity, but the rest have it. Then now you can consider linear functionals that will not give you just a value, say a complex number, but will give you a function. So here L of p will be a function depending on c. And suppose that you also have a derivation. What will be the action of this derivation on the linear functional? Well, you need to ask it to satisfy this equation. So the derivation of the linear function of a polynomial have to go inside and take a derivative with respect to this variable c if the polynomial depends on c, and multiply the polynomial by x. So in particular, if you apply it to the monomial basis, then this derivation is just shifting the moments. And so it gives you a recurrence relation for the moments. Now, if we have a family of, say, monic orthogonal polynomials, we know that the derivation will be a polynomial of degree at most n-1. So we can represent it in terms of the elements of the previous family. And then if we use our definition of the action of this derivation on the functional, we will conclude that all of these have to be 0, all of these coefficients ck, except for the last one, and that one is precisely minus gamma n. And so the derivation of any polynomial in the family is just a multiple of the previous one with coefficient minus gamma n. But this is nothing but the Toda equations in disguise, only that this has the orthogonal polynomial flavor into it. So if we say that this derivation has some matrix representation R, right, and R has pretty much only one diagonal different from 0, then if we relate it to the Jacobi matrix J, we get this compatibility condition. And this has very much two elements that are worth looking at. And they give you the Toda chain for beta and gamma. So the derivation of beta is just a consecutive shift of the gammas, and also the other way around. And so in this way, the Toda chain enters naturally into the field of orthogonal polynomials without any physical interpretation or dynamical symmetry interpretation or anything. It's just completely associated with a derivation and a linear functional. we will not use this much, but of course, since, as we saw before, the sigmas and the betas are related, and also the H's and the gammas, one can get also kind of total relations for them. And so the class of functionals that we are looking at have this structure. They have some function depending only on x times a term that is always of the form c to the x. And so the derivation that plays a role for these families is not the usual derivative, but c times the derivative. Because this is the one that applied to this function c to the x will lower x enough to augment the monomials and give you the next moment in the sequence. And so all the moments can be computed just as that derivation apply n times to the first moment. And so the first moment completely determines the family. If you know that, you know everything that you want to know. Just to see what is the connection between that operator and the regular derivative, you can establish a connection through Stirling numbers of the second kind, because that is also, those are also the numbers connecting the two bases, the monomial bases and the bases of Pochhammer polynomials. Okay, and so what are these generalized Hahn polynomials of type 1? So the weight function is the same weight function as for the classical Hahn polynomials, but now one adds this factor c to the x. The first moment is just a hypersymmetric function, a 2f1, and all the other moments could be computed just by applying this operator n times to it. Now the first moment has a well-known differential equation, and so one can get a formula relating the second moment with the 0 and first one, depending on how one could want to label them. And this differential operator acts on functions of the form c over 1 minus c by giving you what is called a polylogarithm, a generalization of the logarithm. And so if one will apply the nth operator, this del n, to this equation, one will get the recurrence relation for the moments. This is covering it here, but this is a mu n plus 2. Okay? So this is a recurrence relation for mu n plus 2 in terms of the previous ones with quite complicated functions. These polylogarithms are not easy functions to deal with, but at least is there. Another possibility will be to sort of decouple the structure of these higher moments in the sense of tracking the part that multiplies mu0, the place that multiplies mu1. At the end of the day, that's the main difference between classical polynomials, so classical polynomials of class 1, of class 0, and these semi-classical polynomials of class 1, that the two first moments, mu0 and mu1, in the classical case are completely related to each other. And so all the recurrences are for order 1, but for the semi-classical polynomials of class 1 and above, mu0, mu1, and etc., are in the sense independent of each other, and so one has to take them into account, and all the recurrences then increase the order more and more. And so if one wants to track what is multiplying mu0, what is multiplying mu1, one can put those in a very convenient now matrix differential difference equation, which is much easier to compute than the previous recurrence relation involving those polylogs. But as I said before, the monomial basis is not really the best for these polynomials. It's much better to use the Pochhammer basis. And so in the Pohammer basis, the computation of the generalized moments is quite easy and straightforward. And it just gives you a representation in terms of a 2f1. And this calculation can be repeated for any of these semi-classical polynomials, discrete semi-classical polynomials. And so now the generalized moments satisfy a second order relation, but one that is extremely easy, much better than the one involving the polylogs. And for the mixed moments, well, it gets a bit harder. But again, one has these linearization formulas. So in principle, one can compute it this way, even that that is not computationally very efficient. But then if one uses symbolic computation techniques, one can try to find recurrences for these objects. And one doesn't get pure recurrences in n or m, but has to involve this derivation. And so one gets sort of recurrence difference equations for them. And remember that these are the elements of the Gram matrix. And so in principle, if one will want to compute the polynomials that way, one will have to take all of these, put them in some big determinant, and then compute the determinant. But good luck, right? That will be a very, very heavy computation. So what are one possible set of Laguerre-Freud equations? Well, if we use the technique before, now with this explicit pair of polynomials, phi and psi, and we chuck them in this matrix system, out of it will come a system of equations, which in this case cannot be solved explicitly at all. But it contains all the elements that you need to understand the betas and the gammas, and certainly can be used to generate all the betas and gammas. And of course, one could try to simplify this a bit to get equations of lower order. I'm not claiming that this is the most perfect pair. And also, just as in the case with Meixner, one obtains equations for the shifts, the forward and backward shift. And if one will then combine those, one can get difference equations for these polynomials. And so all the structure needed at the algebraic level is there. Now, there are some limits of these polynomials that are interesting. One is to see what happens when C goes to 0, or when C acts as a perturbation of the polynomials. And in that case, the structure is quite simple. And this is a universal phenomenon, by the way. These coefficients are not the same for every family, because, of course, one has the coefficients of the polynomials phi and psi involved, but the structure is exactly the same for all of them. Once we get those, then the betas are just a perturbation around n, the beta n. The gamma n is 0 as c equals 0, and then the next leading order is this times c. And the polynomials themselves can be seen as a perturbation around the Pohammer basis. So this is completely true for all the families. Just replace this thing by whatever it is in the other cases. Or another possibility will be to set the parameter c equal to 1, which is it's very easy to do at the level of the Laguerre-Freud equations. You just set c equal 1 unless you have it in the denominator, and have to be careful with that. And in that case, the equations decouple and can be solved completely. And so you get the recurrence coefficients for the Hahn polynomials. And also, in this case, the recurrence for the generalized moments reduces the order, which is one will expect going to the classical families. And so everything can be computed in this case. However, the question is, are these really all the elements related to the classical Hahn polynomials? And the answer is maybe not so much, in the sense that for The classical Hahn polynomials, one takes one of the parameters, this A2 and the B, related to a negative integer, minus big N, that sort of cuts the family. And so all the sums and everything related is now finite. Here I'm talking about the infinite family. So in principle, these generalized moments are ill-defined. So one has to be careful how to define that linear functional at the c = 1 level. And one nice thing is that then we have a hypergeometric representation for them. So one can take these and using symbolic computation techniques, then generate all the rest and check that all the formulas are okay. So at this point, you are bored and, of course, looking around at the paintings and saying, why are you telling me this? We are experts in Painlevé equations and dynamical systems and random matrices, and who cares about these polynomials? And probably you know already this, but just in case. The reason is that if one would look at that function sigma n, and of course it also happens for the alphas and the betas, but say if one focuses on that function sigma n being the second leading coefficient, then it was shown by Peter Clarkson back in 2013 that that function satisfies a second order, second degree equation, which one can tweak around a bit by doing a shift with sigma. And then that new function S is a solution of the Jimbo-Miwa equation for Painlevé 3. He did it also for the generalized maximum polynomials, and out came Painlevé 5. And so the question now was, what can we say about the generalized Hahn polynomials? And one will expect that being the ones on the upper level, Painlevé 6 will come. And just before the meeting, Galina and Walter did it. And so they found the equation for the sigma n associated with these generalized Hahn polynomials, and no surprisingly, there was also Painlevé 6. And they also have a nice set of Laguerre-Freud equations of lower order than the one that I showed you before. So very nice piece of work. I tried to convince Galina to present the results, but she refused. So you'll have to read the paper. And also there is a very recent book by Walter Van Asse that covers these topics, at least up to the ones that he and collaborators had worked on, but it contains a lot of information. So if you're interested, I think that's a nice reference, a small book, very easy to read. And so far then one could sort of augment the ASCII scheme a bit, put in all these families. So here are the classical ones. And for the semi-classical polynomials of class 1, well, now we know then that the generalized Hahn of type 1 is associated with Painlevé 6. It can be degenerated into a generalized maximum associated with Painlevé 5 and generalized Charlier with Painlevé 3. There has been no work done, to my knowledge, on the ones that we call generalized Krautchuk. Galina has the same name for a different family. And as far as I know, there is no work done on the polynomials that are classical plus a weight. So it could be interesting to know if all of these are also associated with the classical Painlevé equations or not. Maybe Nicholas now has all the answers. And so, well, okay, you have a machinery, right, and you crank it and crank it and crank it. And so with Paco now, we decided to see what happens when you go to class 2. And then the vista is much richer, right? You have a much, much bigger structure. And so far, this is work in progress. We have been discussing things in this meeting. we got 7 new canonical families. It's not important that you see the details, but just to show you how you can keep increasing these weights, and they all maintain the same structure with the Pohammer symbols and this. Sorry, there's a typo here. All of these should be c to the x if we want to keep the same variable. And then at the very top, there is one with argument equal to 1. That always has to happen, otherwise you jump into the next class. But then, of course, one has to also consider the ones where you add masses at the endpoints of the previous class, and now then you have a bunch. So adding masses to the semi-classical polynomials of class 1 give you now up to 12, and then 13, and then 16. But then one could also consider truncations of classical polynomials. So in the Charlian-Maxner case, one takes a functional that goes along the whole set of positive integers, but one could truncate that without changing q of x, just truncating the sum and see then what is the structure of those polynomials. And what could symmetrize. So the same way that one could go from, say, Laguerre to Hermite by a process of symmetrization, one could ask what are the symmetrized Charlier or Maxner polynomials. And so far, we had considered those 23 families. There may be a few more that we will pick up now soon. And the question is now, what is the next set of equations associated with them? So now one will expect that we are beyond Painlevé. So will all of them now be in some new class of Painlevé? One could expect that because all the semi-classicals of class 1 were just contained in the classical Painlevé family, so maybe all of these are also contained in some extension of it, but for that, of course, we don't know anything so far. So anybody that knows already will want to work on that is welcome to. So thank you very much.
Okay, thank you very much. Are there any questions or comments? Okay.
The Painlevé 6, this Painlevé equation, are you taking derivative with respect to some time variable?
Right, the time variable in this case
is z.
Opa. Yeah, z.
Okay, so although the weight is discrete,
it has this continuous parameter
it's a
in the
continuous
c to the
parameter
x
z
part.
or c, and they are Painlevé. That's nice.
You could, of course, transform c into e to the t,
Yeah,
and so you'll have like e to the tx,
yeah.
and then the time will be more explicit
Okay,
as in the
okay.
Painlevé theory.
Thank you.
Okay, some more questions or comments? Actually, I have a question. You showed that the Pohammer basis is more convenient than the monomial basis. Do you expect there are some other bases that might be useful, I mean, from algebraic point of view for computation of moments and recurrence relation?
I have tried, but
It's actually obvious. It's for the Q, it's the Q Pohammer.
Oh, yes, there are about.
The Esty-Wilson type. It's the symmetrized Hahn. I can show you the paper. So all of the Magnus view of the discrete lattices, there are 4 classes, and there's an appropriate basis element for each of them, which is of this. Yeah, thank you. Of this form, yeah, and the next step is, they're all defined because the lattices are the solution of conics, or they're solved by conics. It's a quadratic equation, this is a spectral equation. And the next case up, the elliptic case, is also known. So that's a biquadratic equation, and we know what the basis functions for those would be. be the PQ Pochhammer, elliptic Pochhammer symbols. So, yes.
I mean, just to follow up, I understood the question in the sense of, could one use another basis for the discrete polynomials, so the ones on the, just shift lattice. And for that, I have tried to see if maybe the polynomials at the lower level can be used as a basis for the polynomials in the next level, but things get really complicated. So it seems like the Pochhammers are the best choice.
Okay, thank you. If not, if there are no more comments. 5 minutes break, but it's not a coffee break yet. We have a second speaker of morning session. I have a pleasure to introduce young Chen, who is going to asymptotic gap probability distribution of the Gaussian unitary ensembles and the Jacobi unitary ensembles. Please. No, you have your microphone, sir.
Okay, hi. You see, I want to say something before we start. I got an email yesterday from these Singapore guys, the IMS. They say I need to have a video conferencing to make a presentation of what we want to do for 2020 random matrices Eurasia. So this perhaps good news, right? It's a few minutes presentation. Since it only takes a few minutes, maybe it's okay. You don't need to do a few hours. Yeah, so that's that thing. And the other thing is that I have from Aptica nice box of chocolate. Please share it around while you are listening. It will keep you awake. The sugar will keep you awake. Okay, that's. Okay, this is some stuff that I've done with my student. Su Ling is now at Zhongshan University. Has a Zhuhai campus, and Fan Engui, we probably know him. He's kind of an integrable system person at Fudan University. So this thing appeared in Nuclear Physics B. Here we go, some introduction. I'm interested in Hanker matrix, the determinant of Hanker matrix, which is defined, oh dear, how did that go? The determinant of Hanker matrix, which is defined, you see, you take a weight, a positive continuous function, you take a weight, and then you build a determinant out of the moments. So that's the Hanker determinant, Hanker matrix. And the problem of interest to me, from random matrix point of view, is that it's something called gap probability. So let's take a look at this guy. Now, I don't get the light. There you go. Okay, here it is. This x to the alpha e to the minus x is the gamma density, the weight of the Laguerre polynomial. Instead of integrating from 0 to infinity, I integrate from t to infinity. So it makes things a little bit harder. So eventually, you will see that this object is the probability that all the eigenvalues sits between t and infinity. So the next guy is no lights. Okay.
But you have to use this for scrolling.
Okay.
You have to use both.
You can scroll for me. You want to? No. No. Okay. So the next guy is this is the beta distribution, and instead of going from 0 to 1, you go from 1 to t. So those parameters, so the determinant would depend on the parameter alpha, beta, and t. And I like to know how this thing moves with t when I move t around. It's nice to learn that in the previous talk, those Hahn polynomial, those kind of things. If you move the parameter c e to the t, you write c to e to the t, you still get Painlevé. It's kind of normal Painlevé. Nice to know that. So in this setup, I will be interested in the associated monic polynomial orthogonal with respect to, wow, they jump, huh? Orthogonal with respect to x to the alpha e to the minus x. Instead of starting from 0, it starts from t. And over here, it starts from t and goes to 1, the support of the weight. So this quantity depends on t, and if I move t around, this thing will move around in some way. Now, why am I interested in such things? You see, for if you take n points sitting on the real axis, and you look at this, you look at a Hanker determinant generated by x, the moment, the I plus j moment of the weight, of the deformed weight, then you can write this guy as the product of the L2 norm from 0 to n minus 1 of the polynomial orthogonal with respect to the deformed weight, t to infinity, t to 1 or t to infinity. So the equivalent representation is that one form is the multiple integral from t to 1 in this example, and multiple integral, and so on. Now, let's go back to a very old problem studied by Jimbo, Miwa, Mori, and Sato years and years ago, ancient problem that, you see, I used to read the big paper once a year during Christmas. I'm trying to figure out what's going on. Once a year during Christmas. But now this is a kind of a version of the Jimbo, Miwa, Mori, and Sato. You start with finite n. The matrices size is finite n. Eventually you let n go to infinity in a certain way. So the question that they like to know is eventually you look at this, consider the gap probability in GUE. GUE meaning Gaussian, e to the minus x squared. And then there's a gap between minus a and a. The characteristic function of minus a is 1 if x is in the interval minus a and it's 0 otherwise. So this thing is actually the gap probability is given by this object. So, okay, in this case, in this problem, the weight is even, right, because it's an even function. Then the polynomial would skip 1 degree, px to the n, and the next one down is x to the n minus 2. And there's this object called Pn, the leading coefficient. It turns out to be a very important thing. Anyway, and from orthogonality, we immediately get this recurrence relation. We only have beta n. You don't have the central term. That's because the weight is even. And then we take the initial condition, beta 0, p0 is 1, and beta 0, p minus 1 is equal to 0. And the beta n, the coefficient of Pn minus 1 is Hn over Hn minus 1. It's just classical thing. Everybody knows them. So the parameter t and alpha will appear in the weight, and they will therefore appear, which appear in the weight will therefore appear in the recurrence coefficient. So if you move the t around, the recurrence coefficient will move around. Okay. So now I show something. Yeah, this is something due to Magnus. It's years ago. I find it very useful. This is kind of a variation of Magnus. What you do is that if you take a derivative of this thing, you get degree n and degree n minus 1. So these guys are not the standard recurrence relation, because otherwise an and bn. Yeah, so it doesn't quite work like that. And then these an and bn satisfy these compatibility condition. So what you get is that this function an and bn satisfy S1, S2, and then there's a sum. If you execute a sum, you could you get this sum over AJ. That's actually I find very useful to do all this stuff. Okay, so I call this S1, S2, and S2 prime. So the sum involved the sum of AJ obtained from S1 and S2. In fact, you don't do any sum at all. You just have this thing, it sums the thing automatically for you. This is what I learned at heavy price. Anyway, so here we go. Next thing. Now for this problem, the W0 is the Gaussian weight. The factor in front of 1 minus chi minus AAX. This Gaussian weight is this thing. It's called W0. So V0x is x squared. And you go through a little bit of hand calculation, you find that this AN object is a rational function, that's the point, a rational function with pole at plus A and minus A, and Bn is also a rational function with pole at plus A and minus A. And so okay, what about the residue? The residue are like that. These are very interesting objects. The Rn, this guy, the residue here, up on the An, is the evaluation of the non-standard polynomial because the interval orthogonality is not minus infinity. It's a non-standard guy. This is kind of an operator product. You evaluate the non-standard orthogonal polynomial at A with at n, Pn square, Pn square. And the Rn is Pn Pn minus 1. It's staggered a little bit. Okay, so now if you take these things, if we go back, we put it into this A guy, put it in there, and you shake it down a little bit. Whoops, you shake it down a little bit. So you keep the A parameter fixed, you don't move it. So all these objects here are evaluated at A, a single A, and then you move n around. So you get this is biggest thing is n plus 1, the smallest thing is, so this is a second order nonlinear difference equation. So now the resurgent people can probably tell me how to do this when n is big. I don't know, this is probably useful, right? So anyway, so starting with the initial condition, where is that light? Well, anyway, with the initial condition that R minus 1 is 0, R0 is obtained by some elementary error function, something divided by error function. Now, if you look at the little Rn, you get again a second order nonlinear difference equation. In fact, if you look around, if you move around a little bit, if you let yn to be equal to minus 2 Ran divided by a squared, this object is a particular discrete Painlevé 2. So these are the discrete part of the story. So I'll leave this here, and if people could show me somewhere to work on the asymptotic expansion for n big but a fixed, it would be nice to find out where are they. So okay, now you see your gap, you can write the gap as the chi as theta x squared minus a squared, which is theta x. Theta is the step function. Theta is 1 when x is bigger than 0. Theta is 0 when x is less than 0. So these are the basic, you only get distributional object in here. Otherwise, it's all elementary, it's all linear algebra. If you do that, you take derivative with respect to a, and then you have this Toda-looking thing. You go through, this is just basic calculus. You find that you get little rn derivative with a is a square and little rn is a Riccati equation, and then you take little rn with respect to its rn square, etc., etc. These guys are in fact these things were discovered by Gromach. If you read this green book on Painlevé, Gromach discovered this thing from some other context a long, long time ago. Gromark and Lukashevich. So LTA stands for a long time ago. In the 70s, they were looking at a different problem, different class of problem, but they come to these things. So now the idea is this, is that if you look at this guy here, capital Rn appear linearly. So the instinctive thing to do is to take capital Rn, solve for this and plug it into this equation, and you have this sort of a Painlevé looking thing. Not quite exactly Painlevé, but you get a second order nonlinear differential equation with Rn prime over with all this stuff. You plug it in. Now you can of course also eliminate capital Rn and get a second order differential equation. So if you let nu z equal to minus Rna, where z is equal to square root 2a, this is the fourth member of the Ch2. See, these are all very ancient things. So if you let nu equal to minus Rna, where z is square root 2a, this guy is the fourth member of the Ch2 with parameter alpha 1 and beta 1 and gamma 1, like that. So these things you can find in this guy, Chris Cosgrove. He wrote many things on this Ch, etc. classification. So I got it from there. I understand that Cosgrove has taken early retirement.
Yeah, he's not on the payroll.
He's not on the payroll, okay. Okay. Because he's not publishing 75 papers a year. Because you see, Cosgrove, right, he writes something, you read very carefully, you learn a lot from him. Yeah, it's a huge papers, yeah, deliberative, scholarly paper. You learn a lot from Cosgrove. Well, at least I did. Anyway, there you go. Now we call this sigma function. You see the things that the probability is a Hanker determinant. The Hanker determinant involves product. So the Hanker determinant is actually the partition function. Okay, so if you take the log of the partition function, you get something called a free energy. So I call this guy sigma. Now, if you keep A fixed and move, because those objects move in n in a certain way, we found this discrete equation for the sigma. This is possibly new. Anyway, the question is that what can one do with this discrete equation? Anyway, so these are this discrete thing. And next, now we keep n fixed at a particular value, some n, and you move A around using the differentiation formula. If you work through this thing, this guy is a kind of a monster-sized second order, second order degree 2 thing, isn't it? Or degree 3. These things is actually not a Painlevé equation. It's just this animal. But Jimbo, Miwa, Mori, and Sato, they already started with the double scaling. So you don't see this kind of thing. So now I go to the next thing. Okay, now we do this double scaling thing. Jimbo, Miwa, Mori, and Sato. You let A go to 0, n goes to infinity in such a way that this parameter tau is fixed. This is the famous double scaling thing. Essentially what you do is that you increase the number of particles and you decrease the size of the gap. You make the gap as small as possible such that this particular product is fixed. And if you do that, this monster equation zoom down to this the famous JMMS sigma form. Now, in a paper my previous student and I wrote, is that if you keep, this is the original sigma form, we could systematically keep the 1 over n squared term in the big equation. You do this double scaling. This 1 over n squared appear as coefficient. So when you let n go to infinity, you're just left with this. So this is the Jimbo Miwa sigma form. So we wrote something in another paper, but never mind. So now how do I do this thing? Now I decided to do it this way because the chi, 1 minus chi minus AA is theta x squared. So I double up. You see, what I do is I double up because essentially the weight is even, so I can look at H2n and H2n plus 1. H2n, H2n plus 1. So you see, if I double it up, I get integral from A squared to infinity. This is actually what Jacobi did when he studies the asymptotic of the Hermite polynomial. He takes the Laguerre polynomial, he takes alpha equal to plus half and minus half. And you do this doubling up. So this is what we do. You double up the interval. So because of this gap thing, you go from A to infinity, A squared to infinity. H2n plus 1 is this thing. They are P Twitter and P hat. So P Twitter and P hat are polynomial of degree n in T. So now we look at the distribution of the smallest eigenvalue distribution of the LUE. So you are integrating from A squared to infinity. And the weight is LUE, but with the parameter alpha equal to minus half and alpha equal to plus half, right? If you double them up, you get this, not general alpha. So what we do is that we look at the LUE, but we keep the alpha general. We take alpha equal to minus 1/2, so that things are integrable, the moments exist. And this object, dn0 alpha, when you close the thing, can be evaluated by Bunch G function. This is a very famous thing. You see this, the L2 norm, the product of the L2 norm, square of the L2 norm at t equal to 0 can be evaluated by hand. You just multiply them together. You make use of the definition of Bunch G function. You get this Bunch G function. But note the n. Okay, this is again finite n thing. All of this in some way is linear algebra of the integration by parts. You see, yeah. So, okay. Now, to continue, I would like to look at the Hahn formula for the monic orthogonal polynomial respect to x to the alpha e to the minus x over t infinity. So this is the Hahn formula. You stuck a linear term in here. Right? The Hahn formula will give you the monic orthogonal polynomial because I divide by d and t, so I get this monic orthogonal polynomial. And so Pn, the evaluation of the non-classical polynomial at 0 is dnt alpha plus 1, because if you take t equal to 0, if you take t equal to 0, you put z equal to 0 here, and then if you take z equal to 0, this object disappear, then you have minus x to the k. It boosts the alpha factor by 1. X to the alpha, you boost it by alpha. Okay, so this is alpha plus 1. As a consequence, this gap probability now is gap probability at alpha plus 1n and gap probability at alpha n. But these objects are expressed in terms of the monic non-classical orthogonal polynomial. Okay. Now you need to know something about this P and 0t alpha. They're the non-classical thing. But anyway, let me continue with something else first. Now, okay. So if I call sigma t to be equal to t ddt log p n t alpha n, you go through the cranking out, you find that this is the Jimbo-Memoir sigma form of a particular P5 with the Laguerre weight. So because of the alpha. So now this Jimbo-Memoir sigma form for the particular P5 can be, the sigma can be expressed in terms of those R quantity, the residue. Okay, so this is also classical. So now I want to do the following thing. I want to let n go to infinity, t goes to 0 such that S is 4nt, not too big and not too small, so it's fixed. So if I do that, this object becomes the sigma form for sigma S satisfies the P3, and I can therefore write my log of the probability as an integral from integral of in terms of those R. Now, in order for me to do, you see, I like to look at the large S expansion, the large gap expansion. Now, in order for me to do the large S expansion, I have to know something about this guy, capital R, when S is very big. You see, this is something that I learned. If you let S very big, this derivative guy don't do too much. You see, they don't do too much, and then you have some equation, you solve the equation, expand in S, you get these things. Now, if you assume this expansion and plug it into the original equation, there are little minor modification of the coefficient of the large S expansion. All these things are done by hand. Okay, now you take this thing and stick it into here and do an indefinite integral, so they give you a constant. So here we go. You integrate these things, plug it in here, you integrate, you have S square root S log S. This is an interesting thing that I didn't realize that this log S would show up because I did some other tricks, other stuff that you never see the log S, but in this case the log S show up automatically. So you get this constant term when you integrate as an indefinite integral, because this has to be an indefinite integral because you plug in the asymptotic expansion into integrand. So you have some constant here, C1 alpha. So now we have to figure out what this C1 alpha is. So S square root log S, if you exponentiate the P, you get 1 over S alpha square over 4. These are the power law decay, the slow decay term, etc. And then you get the constant. So now we make a note. If I remember, PS alpha plus 1 over PS is Pn0t alpha and this thing. So then you get a difference, a linear difference, C1 alpha plus 1 minus C1 alpha. So you have to somehow figure out what this constant, the difference equation is. Now to do this, we need to go to this equilibrium problem. Yeah, this is n very big, you go to equilibrium, you describe the eigenvalue by a certain density, rho. This density rho would satisfy the variational equation of the Voigt-Kovalevsky entropy, or the Dyson-Coulomb energy. Is now known as the Voigt-Kovalevsky entropy. Okay, so you solve this singular integral equation, you get this solution, and then you plug it in here, plug it into this standard singular integral. You get this object. So here the V is the minus alpha log x plus x. You plug it in, you integrate, you get this thing. Now, because my density has to be positive, so I require square root TB is greater than alpha. This is satisfied. So the density is positive. So next, and then I now need to find a relationship between T and B and N, because I normalize this thing to N. There are N particles. If I normalize this thing to N, which is this equation, and I clear the square root and all that, I get a cubic, right? I have a T square, T, and this is a elliptic curve. When I gave a talk in China, some of these algebraic geometry, they say this is actually very interesting because this is a cubic curve. Because you get a cube here, right? B square and B cube, and you get a cubic curve. So now, another thing is that somehow I need to find out what B is. This is you see, I learned this thing from Optikarev. You see, Chebyshev, long time ago, shows that the alpha n, the diagonal recurrence coefficient, in this case is the Laguerre weight, the diagonal recurrence coefficient is not 0. Diagonal recurrence coefficient is the center of mass of the interval. The interval is t and b, the center of mass is t plus b over 2. So, but from the previous stuff that I didn't write down, those compatibility conditions, you get a direct expression expressing alpha n in terms of this capital R. So this is pretty good. And so essentially you now cheat a little bit. You take alpha n is b plus t over 2. You plug it in here, so you get b is equal to 2 alpha n minus t. And you have this equation. Now, we have this thing less than that. The last equality was due to Rn less than 1. We can give a proof. Okay, so there we go. Yeah, so this is what people call the Voiculescu entropy. You see, you have some log repulsion and some V, something that confine those guys together. So this is, but now it sits between one interval between t and b. You have to make certain assumption. Okay, you assume this thing sits between t and b. Okay, so you go through this thing, and so the detail is that then you do a variation, vary this with respect to epsilon, keeping the thing fixed. You need a Lagrange multiplier, which fixes the constraint t to b integral is equal to n, and then you take a derivative, you get a singular integral equation. And then you look at classical text. So this is how the rho was obtained. You solve the singular integral equation, you get the rho, and then now you have this thing. You let t n large, t positive. You get this thing. And next step. So what you get is you have this b is 4n plus 2 alpha. 4n plus 2 alpha is the classical thing if there's no t to talk about for the Laguerre. And these guys are 1 over n expansion, where s is this parameter. So anyway, okay, now I need to, so this is the crunch. The crunch is that I need to find out the orthogonal polynomial evaluated at t equal to 0, the non-standard one. So this thing here is something I produced a long time ago with my student. You could solve some singular integral equation and get this result. Now, recently, I was doing something with somebody from Lancaster, this guy called Gordon Blower. And these things actually were obtained by the free probability people, 2010 or something. So this is okay. It's not completely insane, right? That's the point. Okay, so you obtain this S1 and S2, and you exponential, you do some calculation, you discover that minus 1 to the n p0 evaluated at 0 n t alpha is given by this object. You see, you look at these things, n to the n, etc., it's kind of like a Stirling formula. Okay, now, remember, if you look at the Stirling formula, n over e to the n is asymptotic to gamma n plus 1 plus alpha divided square root 2n. So now you trade this thing, this funny n to the n thing, by the gamma function. Okay? Now, next. I think the pure mathematician would be very upset, but never mind. So anyway, let's go on. So now, okay, now I evaluate this. I know this thing, right? This, for t equal to 0, I know everything exactly. This Pn 0 alpha is d n 0 alpha plus 1 over Pn 0 alpha. So this thing can be calculated by hand. Go to Zego and get it. This is a classical thing. And so you see, you divide out this gamma n plus 1, and then therefore you have this object. So you have this a log gamma n plus 1 square root 2 pi, etc., etc. So therefore, you compare with the previous slide, you know that C alpha plus 1 minus C alpha is this log gamma 1 plus alpha over square root 2 pi. So this is exactly the Barnes G function. You see, this difference equation, okay, we need some uniqueness thing. We need to somehow give an argument at this solution. This is a linear difference equation. You integrate the linear difference equation. This is the Barnes G function. Okay, that's the idea. Okay, so now, okay, now we go to the GUE. The GUE is actually corresponds to the case for the Laguerre polynomial for alpha plus 1/2 and alpha equal to minus 1/2. That's in the original approach, the JMMS approach, you write the probability as determinant I minus some kernel. The kernel is the psi kernel, very famous, because if you take the Christopher double kernel, you let n go to infinity a certain way, you get a sine kernel. This is a famous Japanese thing. So JMNS have this result. Under double scaling, if we do that, you have these interesting, very interesting constant, 3 zeta prime minus 1, etc., log 2 over 12, etc. This constant was obtained by Harold Witham in 1973 on Topliss matrices on the circle. The symbol, instead of 1 over the circle, is 0 over an arc. So you change the arc into the line. This is the famous Harold Witham constant, 1973. And Dyson did this thing using inverse scattering approach, Marchenko, Lavitan, this is a thing. And I mean, rigorously by Thorsten Erhard, 2006. It's not a trivial thing, right? You do that, okay? There we go. Now, therefore, so recall, now we go to the constant. DNA is related to the smallest eigenvalue of the LUE with, so the twiddle guys are the minus 1/2, when the alpha is minus 1/2, and the head guy are the alpha equal to 1/2, and you multiply them together accordingly, twiddle and for n equal to 2k plus 1 and n equal to 2k. So this object now is the twiddle guy divided by twiddle k, head guy divided by head k, and so this thing, if we continue, these are just p alpha squared minus 1/2 p b squared minus plus 1/2. You take the log, and the constant is here, right? Because the previous thing gives me some constant, I don't know. So these two constants, c minus 1/2, c 1/2, you see, this thing here, I would express in terms of Barnes G function, g minus 1/2, g 3/2, etc., blah, blah, blah. This is, you see, g 1/2, Voros, long time ago, I think Voros is in, maybe retired? Voros in France. Voros? Yeah. Huh? It's in Saclay, it's still in Saclay. Okay, Voros, many years ago, wrote these things. He shows that g 1/2 is evaluated as 3 zeta prime minus 1 over 2 pi minus quarter 2, etc., and then therefore you identify, I identify c minus 1/2, c plus 1/2 as log 2, 3 zeta prime minus 1. You need a lot of machinery from many years ago, because how the hell am I going to know that g 1/2 is this? This is a famous result due to, he has many famous results. If you read this paper in Communication and Mathematical Physics, he gives you this very interesting identity. Spectral function, spectral determinant, something. Communication, Mathematical Physics. So anyway, so now I look at JUE. Probably that all eigenvalues are in t and 1, so I integrate between t and 1, and then I go through this business. You see, the thing is that when you write down the sigma function equation, the beta parameter does not show up. This is a bit shocking. We checked this a few times. You see, if you look at the sigma equation, there are two parameters, alpha and beta, but beta does not want to show up. I think this is correct. So anyway, you go through this thing, same argument, you have this C2 alpha comma beta, some constant. Certainly depends on alpha and potentially depend on beta. So what we did is that we managed to find this constant for alpha and beta. Here we go. We go through more or less the same idea. We need the linear statistics, this is Jacobi theorem for the orthogonal polynomial, and this thing shows up. So there we go. This is maybe a little bit too fast. Ask more questions if you like. So these are the things that we wrote, and yeah. So Cosgrove has a nice extensive paper in Journal of Physics 8. You learn about the Chasey second degree Painlevé, this kind of thing. Finished.
Are there any questions or remarks? Actually, I have one. Could you go back one slide back?
Oh dear, yes, the chairman is it's gone now.
Oops.
We're not allowed to go back.
No, it is possible.
Well,
it should be.
It should be possible. Ah, okay.
It's invertible.
Yeah.
But the last but not.
Another
the
one
last,
before.
No, the last.
Next one.
No, the one where. Oh.
This one.
I have no idea. There was a list of references and
there was a list of reference.
Yes, go.
Yeah.
Oh, yeah, and one back.
And then one back.
Yes.
Yeah.
You said that you were surprised that beta is not. Oops,
you see, the beta did not appear
but
in the sigma equation.
But I think the reason is that that you make what? You take t away from 0.
Yeah.
So
yeah.
alpha is more important than beta, right?
Yeah. But
that's why I think it's natural
that's
that
okay.
beta
That's
doesn't
a
show
good
up.
explanation. Yeah. Because I'm getting t away from 0.
So the
the
beta doesn't count, I think, in this part.
You see, the next thing that I'm interested in is that you take this classical thing, instead of integrating from 0 to 1 or 0 to infinity, you integrate to something. These are the soft edge. The soft edge has another constant. I have not figured out how to calculate the soft edge constant. Torsten calculated them. It's sort of operator theory. He turned this Hanker determinant into Topliss determinant in some quite gigantically complicated thing. And then finally, you get the soft edge constant. I'm very interested in finding out the soft edge.
Some more comment? Oh, there is one question. Are there any chocolates left?
Sorry?
These chocolates that you gave away, maybe there is some left for you.
Yeah. The chocolate you passed around already, right? Yes. Fine, good, fantastic.
But if there are no questions, let's thank the speaker again. We have an extended coffee break, I think. Where's coffee? I have no idea, but when I think we meet at 11:30.
We go downstairs for coffee.
Yes, until 11th. I'm sorry. 11:30. Yes, exactly. Okay, so the first speaker after the coffee break and the last speaker, but not least, on this workshop is Eugene Kanzieper, and he's going to talk about noise analysis of eigenlevel sequences in quantum chaotic systems.
All right, thank you. So we arrived at the last talk of the conference, and somehow this talk will not be sort of a mainstream talk for this conference, because probably I'm the second physicist here in the audience. So I wouldn't develop any new mathematics. What I will do, I will show how the recent advances in the theory of integrable systems and recent advances in analysis of infinite dimensional determinants can be used to solve a practical problem in quantum theology. So that's the title of my talk, Noise Analysis of Eigenlevel Sequences in Quantum Theoretic Systems. It is based on a joint work with my very first postdoc, Volodya Osipov, who is currently in the University of California, and the last postdoc, one of my two last postdoc, Roman Reiser, which is now at the University of Haifa. This research was supported by the Israeli Science Foundation, and the paper was published already a year ago in the Physical Review Letters, and somehow we were quite surprised to discover that it was highlighted as the editor's suggestion. So since then, we are struggling to write a longer paper of some, 40, 50 pages, because there's a lot of mathematics involved. But of course, here during the talk, I don't intend to give many mathematical formulas, many derivations, perhaps apart from one, the central one derivation, but it doesn't require much mathematics. Okay, so that's the outline of my talk. In the introduction, I will introduce two universality classes in quantum theology, given that there are probably many experts in the field. It will be on a very elementary level. And then I will, and these two universality classes refer to two different types of spectral statistics in quantum systems whose classical analog is either chaotic or regular, and I will explain that in what follows. Afterwards, I will remind about two large classes of level spacing distributions which characterize these two universality classes in quantum theology, and will pay special attention to the Painlevé representation of the level spacing distribution in quantum theoretic systems. And the reason is that in the very end, once I solve a particular problem of my interest, we will see that not the same, but the fifth Painlevé transcendent is in our final answer, but in a more complicated form. All right, so after this introductory part, we will go to the more or less central part of the talk, where I will introduce a new way to characterize the spectral statistics in quantum theology. I will define a new statistic. It's not really new. It was defined or introduced in 2002 by some Spanish group, but since then, lots of work that was done in the field was sort of controversial. And what I will try to argue is that the theory that the people invented suffer from some inconsistencies, and I argue that it can be revised, it should be revised, it can be revised, and after all, we would be able to find an exact solution to the problem, which will be expressed in terms of the fifth Painlevé transcendent, and afterwards we will do some numerics and see how our results compare with the previous theories and how they compare with experiments. Okay. And when I'm talking about experiments, it will be sort of a numerical experiment for random matrices, and in the very end, some results for zeros of the Riemann zeta function, and it will be very interesting, at least for us. It was quite unexpected. Okay, so that's more or less, so power spectrum for zeros of the Riemann zeta function is the work in progress, and will be the last station of this talk. Right, so let's talk about the two universality classes in quantum theology. And in principle, the quantum theology studies the statistical properties of quantum systems whose underlying classical dynamics is either regular or chaotic. And by saying that, I mean the following. So to be concrete, let me just flash here, say two extreme types of billiards. There is something in between as well. But first, what I want to show is this is, oh my goodness, I'm sorry. I really apologize. Okay. So the first thing that I want to look at is this circular billiard. Okay? And I want to think about this billiard in terms of classical mechanics. So if it is classical mechanics, so I may think about some point-like ball moving inside the billiard, this one, the circular one, and we see that the trajectories of the particle are very regular. There's a good reason behind this observation, because there are two conserving quantities, which is the energy and the angular momentum. On the other hand, if we go to the another extreme, which is the cardioid billiard, we see that, and of course the movement of a particle inside the billiard is determined by the shape of the billiard. Okay? So we see that in the cardioid billiard, the trajectories of the particles are chaotic, and in particular it means that if we had two trajectories which were very close to each other, then as time goes on, the distance between these trajectories will grow exponentially fast, and that means more or less that the particle that was injected into such a billiard with the time will explore almost uniformly the entire available space. We see here in between sort of a mushroom billiard which has a mixed phase space, so we see that a part of the billiard shows the regular dynamics and the other one is chaotic, but we will not be here. We will be talking throughout the talk about these two extremes. Okay. So we trying to think about these two billiards, circular and cardioid, in terms of classical mechanics, but quantum chaology wants to know what's going to happen once we describe these billiards quantum mechanically. And to describe it quantum mechanically, what we need to do is to write down the Schrödinger equation supplemented by specific boundary conditions that we want to apply. And we want to know the spectrum, say, of an electron which moves inside this or that billiard. Okay, so once we have the spectrum, we may treat it as if it is a random spectrum, and we'll try to study the statistics. The most common statistics used in this field is the distribution of level spacings. So this is the way to define such a statistics, and we will be interested in the Largen limit. So we want to know how such a function will behave in the Largen limit, and we assume that such a Largen limit does exist. Okay. Now the question is, suppose that we know the distribution of level spacing for some quantum system. What can be said about the underlying classical dynamics of such a system based on the information that we have in the distribution of level spacings? So put differently, in quantum chaology, we want to know what is the relation between classical behavior of a system and between quantum behavior of the system. Okay, so there is a conjecture by Berry and Taber that goes back to 1977, which tells that eigenlevels of generic quantum systems with completely integrable classical dynamics, and here is an example, will exhibit statistics of a Poisson-point process. In particular, the level spacing will behave as the waiting time between two consecutive events. So that's a claim which is also supported by numerics. For example, here in this graph, I plot, which was taken from some paper by Baker 2007, where you see the numerics for the spacing distribution in the circle billiard. And we see very well that the numerical data are described in a pretty accurate way by the exponential distribution. Okay, so that supports the claim by Berry and Taber. Another example is a rectangular billiard when the ratio between the sizes of this rectangular billiard is rational. Again, here, if one does the numerics for the distribution of level spacing, again, we see that the numerics fits very well the exponential distribution. Okay. So what's going on with the quantum systems which are chaotic in the classical limit? For this case, we have Iberhiger's Giannoni-Schmidt conjecture, and it basically tells that eigenlevels of generic quantum systems with completely chaotic classical dynamics, and here we may think about this cardioid billiard, exhibit the radiometric theory statistics for the proper symmetry class. One of the outcomes of this statement is that the level spacing distribution in quantum system whose classical counterpart is chaotic should be described by the Painlevé 5 transcendent, a well-known result, or some physicists like to use so-called Wigner surmise to describe the level spacing distribution, but it should clearly be understood that this is the approximate result, the Wigner surmise obtained from the 2x2 random matrices, and Painlevé 5 representation is the exact one. By the way, the accuracy of the Wigner surmise, as far as I remember, is just 2 or 3%. So it's very good approximation to the Painlevé 5 exact solution. Okay, here is again numerics, which shows you that, for example, if you have a cardioid billiard and study the statistics of level spacings in such a billiard, then you see that the numerical data confirm very well the Wigner surmise, which is, of course, as I said, is not an exact result, but it's described numerically very well the distribution. Right, at this slide, I just summarize what we know and also highlight one important thing, or maybe two important things. So if we have a quantum system whose classical limit is regular, then the distribution of level spacing would be Poisson or exponential one, depends if you're a physicist or a mathematician. And in case of quantum systems whose classical dynamics is chaotic, the distribution of level spacing would be this function, which is Painlevé representation. Okay. Now, important thing for me for what follows in the talk is that here, once we talk about the distribution of level spacings, it can be represented as a second derivative of such an exponent, and this exponent has a simple meaning of the gap formation probability. So it is the probability that the interval of the length S contains no eigenlevels. Okay, so out of all the sets of these probabilities that the interval of the length S will contain 0, 1, or 2, or whatever number of eigenlevels, only E0 contributes to the distribution of level spacing. And the equation that you see here is the fifth Painlevé transcendent. It should be solved at nu equal 0. It's just some family of equations. So we need to put here nu equals 0, and of course, add the boundary conditions. So two things, again. So the distribution of level spacings is basically determined by the gap formation probability, so by the probability E0. That's one thing. And the other point is that the gap formation probability depends on the correlation functions of all orders. So here Rp are the p-point density correlation functions. Okay, so in this sum, we see the contribution of all of them up to infinity. Something that is very important for me in the next half an hour. Okay, so that was the traditional way to describe statistics of spectra. So the basic quantity is the distribution of level spacing. And again, if we look at the formula for the distribution of level spacing, which is the second derivative of the gap formation probability, so we see that only the gap formation probability enters, and this sort of suggests that the distribution of level spacing is a characteristics which fills correlations between adjacent levels. Okay, so there is no contribution of E1, E2, etc. Okay? Right. So in a sense, now we know that if we have a quantum system and we manage to measure or calculate the distribution of level spacings, and depending on the result, we may claim or we may expect if the underlying classical dynamics is chaotic or regular. In 2002, there was a numerical paper by a Spanish group, Rilano and some other guys, who invented a different approach to describe fluctuations of spectra in quantum chaotic system, in quantum chaology. And I will explain you what this method is and what their results are, both numerical and analytical. So what they suggested to do is to do the following. So you have a set of unfolded ordered eigenlevels. You may think of the eigenvalues of a random matrix if you wish, but not necessarily. You unfold the eigenlevels in such a way that the mean spacing is 1, something which is very common in the random matrix theory business. And afterwards, you define a set of deviations of the J's eigenlevel from its mean. So that's a new sequence of deviations, delta epsilon 1, delta epsilon 2, etc. And delta epsilon L, say, is epsilon L minus its average. Okay? The crucial step is to say that now let's consider this sequence of fluctuations of ordered eigenlevels as a discrete time random process, so that at times t equal 1, the random process takes a value delta epsilon 1. At times t equal 2, it takes a value delta epsilon 2, etc., until t equals n. Okay, if that is what we do, it makes sense to define the discrete Fourier transforms. I hope you can see it. So that is the way to define the Fourier, discrete Fourier transform for the sequence delta epsilon j. And afterwards, as it is usual to do in the theory of random processes, we will define the power spectrum of such a a power spectrum of such a discrete random process. I'm sorry, and not here. Where we are, here we are. Okay. So they wanted to consider or to study the behavior of this power spectrum as a function of omega k. They wanted to do it, and they did it for systems with chaotic classical analog and with regular classical analog. Before I present the results of the numerics, I want to talk a little bit about the special statistics, which is the power spectrum, because it's sort of very peculiar. For example, if we have a look at the definition of the power spectrum, what we may see is that if omega k here, okay, and omega k here is 2 pi k over n, k are integers, and omega k can be taken from the interval from 0 to pi, more or less, because of the symmetry properties of the power spectrum. So if omega is of order 1, then it can be seen from the definition that only eigenlevels which are not very distant from each other will contribute to the power spectrum, because otherwise when j minus L will be of order n, and the number of eigenlevels is supposed to be large, then due to the oscillations, the contribution of such eigenlevels will be washed out. On the other hand, if we take omega k's, which are much smaller than 1 here, then we see that they will have a significant contribution, or we may expect that there will be a significant contribution of eigenlevels for such eigenlevels for which j minus L could be of order n. Okay? So that means that this is very peculiar statistics, such that if we tune omega k from 0 to pi, we may sort of see the correlations between nearest eigenlevels or between distant eigenlevels, and it depends how you tune your omega k. And this is something which makes it different, for example, from the distribution of level spacing, which is a local statistics from the very beginning. Let's take a look at the numerics. So this is the numerics of the Spanish guys. So what do we see here? So what they did is the following. So they have taken 3 ensembles of random matrices: Gaussian orthogonal, Gaussian unitary, Gaussian symplectic. They did the rescaling of the spectrum and calculated the power spectrum, these functions, average of a different realization of random matrices. What they observed is that in the log-log, I'm coming there in a minute. So far we are here in the random matrix theory stuff. Okay? So what they found is that if they plot the power spectrum against the frequency in the log-log scale, they immediately see sort of a linear dependence such that basically they observe in the entire region of frequencies the 1 over omega dependence. So alpha for these 3 random matrix models is more or less 1. On the other hand, if they take the ensemble of Gaussian distributed diagonal matrices, which should mimic properties of quantum systems with regular classical dynamics, then again they have seen the linear dependence in the log-log scale, but the exponent alpha was 2. Okay, so then they repeated the calculation for some other systems, for example, for the spectra obtained in the shell model in magnesium and yttrium. Again, what they have seen, and these systems are known to be a chaotic system, they observed that, again, if they calculate the power spectrum, they see the 1 over omega dependence for the entire region of omegas, and alpha here somewhere downstairs. The alpha here is this one. Again, very close to unity. Then they try to study the real, so to say, system, which is rectangular billiard. Again, they calculated the power spectrum and found, again, the dependence 1 over omega squared. So then they claimed sort of a new universality. They are saying, okay, so if we want to study to what type a quantum system belongs, let's study the power spectrum. Let's study the behavior of power spectrum as a function of omega. And if we see the 1 over omega dependence, it should mean that the underlying classical dynamics is chaotic. And if it is 1 over omega squared, then the underlying classical dynamics should be regular. What was strange for me is that given the quite a complicated definition of the power spectrum, in a moment I will flash it again, the final answer is so simple. So it's 1 over omega square. How could it be? That was my first question once I read these papers. Okay, let's look at the derivation that these guys provided in 2004. So the basic, so in this paper, they wanted to build a theory that would explain 1 over omega and 1 over omega square dependencies in the power spectrum. And the treatment was pretty trivial, I would say. So first, they used so-called form factor approximation. And not only they, but the entire set of papers in the field until a year ago used the very same form factor approximation. So what is this form factor approximation? First, I define here the spectral form factor, k beta tau. Beta refers to the symmetry class in random matrices, so it is 1, 2, or 4. And by definition, it is the double Fourier transform of the density-density correlation function, which could be written equivalently in such a way, whatever you prefer. The major claim of the theory that they published and all other theories that came afterwards is that the power spectrum can be expressed in terms of this spectral form factor. So they have some relatively lengthy expression it doesn't matter for us at this moment, but the important point is that their claim is that the power spectrum can be expressed in terms only basically 2-point correlation functions, which was sort of strange. Anyway, so I'm saying I don't want to study the entire formulas that they give. I want to go to a very specific limit, and that's limit of small frequencies. So I want to know what's going to happen to their formula once omega k here is much smaller than 1. And again, I just remind you that omega k is between 0 and pi due to the properties of the power spectrum. So that's a limit that follows from their general expression, and I really want to examine what this limit gives me. Okay. It is known that if you are in a quantum system which has regular classical dynamics, then the form factor is just unity. I plug it in, and I get 1 over omega k squared, trivial substitution. On the other hand, I don't need this a particular approximation to calculate the power spectrum in this particular case when the statistics of level spacing is just the exponential one, something which is known. And so I may calculate directly the power spectrum just starting from the very definition. The answer that I get is 2 divided by omega k squared. So this is a factor of 2. So my question is where it comes from. And because the basic assumption of the approach is that the form factor is that the power spectrum is determined by the 2-point correlation functions, so I bet that the additional factor comes from the high order correlations, which for some reason they didn't take into account. Okay, I'll go further on, and now I'm saying, okay, let's see what this formula brings to us if we are talking about quantum systems with chaotic classical dynamics. In that case, there is a famous randomatic theory result that tells you that the form factor behaves in such a way for small tau, and that is what we need. And then their formula brings me such an answer. It brings me such an answer, and I know that it is correct. It is correct. It is correct in the omega k much smaller than 1 limit. Okay? Otherwise, their formula, which I didn't write here, will bring you some expression, but at least what I know from the further analysis, that in the limit omega k much smaller than 1, this is the correct result. Of course, there are corrections, and by the way, these corrections cannot be obtained from their general formula. So anyway, at that point of our study, we wanted to know what is the status of this result, because if we are going to the regular classical dynamics, there is a factor of 2 which was wrong. So how can I trust this result? Okay. So what I want to say at this moment is that if we want to build a consistent theory, we perhaps need to go beyond the 2-point correlations. And that is precisely what we want to do. Actually, it turns out to be very simple to show just by exact manipulations that this, which is a form factor approximation, what you see here is just k of omega k over 2 pi. So this is the approximation, but in fact, starting from the very definition of the power spectrum, it's possible to rewrite it in such a form. Let's compare the two. So what is the difference? The prefactor is the same. The double integral is the same. What is different is the objects that we average here. So if I compare this with their approach, I see that they are missing some additional vertex which is fluctuating. So I need to average a very complicated object, which is the product of two fluctuating densities at 2 different points times the exponent, which itself, oh my goodness, which itself contains the fluctuating, which itself contains the fluctuating density. So the claim is that if we want to build an entire theory, and of course, if we just say that we are interested only in the most divergent part of the power spectrum, then perhaps it could be justified to put omega k here 0, and then we are back to their result. Again, I'm not saying that this is the right thing to do, because we also need to estimate for what omega k's we are allowed to do that. Okay?
And you get a factor of 2 exactly as well.
Right, but it's factor of 2 in the case of integrable classical dynamics, and it looks like almost everything is fine in the random matrix theory limit. So I want to know what is the status of all this stuff. I'm just saying that the exact approach should be based on this thing, which is not a trivial object to evaluate. And actually, I wouldn't evaluate this object because there's another way to proceed, and that is what I'm trying to explain in several minutes. Okay, so the first thing that I wanted to say here is that the existing theory does need a revision, and we also know where is the point that should be improved. And these are high order correlations that should be taken into account in order to calculate this strange object, the power spectrum. Okay, now what I'm going to do, I'm going to present this non-perturbative theory, and it will be very general. So I wouldn't do many calculations. I wouldn't go to random matrices. I will make a few assumptions about the spectrum in order to get the formula for the power spectrum, which will be quite nice. It will be quite general, and it will not be restricted to random matrices. Okay? So let me show what I do. So I'm saying the following thing. So that's the definition. I hope you may see it. That's the definition of the power spectrum as a function of omega. It's convenient to introduce a new notation. E to the power I omega will be z. So instead of that factor, we will have here z to the power L minus m. And then I want to define a very specific sequence of, a very specific spectral sequence, the one in which the level spacing will be stationary. That is what I wanted to demand. Again, it's not the must to do that. For example, if we are from the beginning working in terms of random matrices, almost everything can be done, or probably everything can be done without this demand. But I do want to impose such a restriction because it makes it possible to make a very general derivation. Okay? And afterward, if I want to go to random matrices, I just take the general result that we will derive here in a few minutes and infuse the random matrix theory information. And if I don't want, and I want to stay in systems with integrable classical dynamics, I will take precisely the same formula, will infuse information about the spectrum in such a system, and again, we'll get everything we need. Okay, so what I demand that the sequence of eigenlevels will be such that if I build a sequence of spacings, first the arbitrary spacing is 1, which is unfolding. The other one is that covariance matrix of spacings should be a function of the difference between the indices. And in general, if we are talking, for example, about random matrices, this property will be expected to hold if we are going to the limit of very large random matrices. But in what follows, I will show you a specific random matrix model where such a property is fulfilled even for finite m. Okay, so it's not a big restriction that I ask here. Once we demand that the sequence of level spacing will be stationary, it's easy to prove the lemma, which tells you that the sequence of spacings is stationary if and only if such a thing takes place for q equal 1 and 2. Okay? So if we have some spectrum, and we may prove there that epsilon L minus epsilon M raised to the power 1 average is the average of the epsilon with the index L minus M. And if we may prove the same for q equal 2, then we are guaranteed that the sequence of level spacing will be stationary. Okay? Great. Now, suppose, and that was our restriction from the very beginning, that we have eigenlevel sequences with stationary spacings, then out of this lemma number 2, we may easily find that the cross-correlator fluctuations, delta epsilon L, delta epsilon M, can be expressed only in terms of variances of the L's, M's, and L minus M's eigenlevel. Why it is important for me? Because now what I'm going to do, I want to plug it, this delta epsilon L, delta epsilon M average, back here, back to the definition of the power spectrum, and see what simplifications I do get. Okay. It turns out that if that is what I do, then there is one sum, for example, over M, that can be performed explicitly, and then the result, and then we get a very nice formula for the power spectrum. Let's take a look at it. It basically tells us, okay, that the power spectrum is some operator which acts on the generating functions of variances of ordered eigenlevels. For example, from here, it's easy to see what's going to happen to the power spectrum of a system with regular classical dynamics. There, the variance of epsilon L is just linear in L. You sum up it, you calculate, you apply this operator, and what you end up with is 2 over omega k squared instead of 1 over omega k squared. Okay? In the small omega k region. But you, of course, may write the entire answer for all omega k's from 0 to pi. It will be a little bit more complicated. But the fact is that in the small omega k region, you do have this factor of 2. Okay. Not enough for me, because dealing with variances of the L's ordered eigenlevel in random matrices is not that good. So what I want to do the last trick. And the last trick would be the following. So let's define the probability. My goal now is to calculate this sum, or let's put it differently. I want to rewrite this sum in a more appealing form. So I do it in the following way. So I'm saying I need to know the epsilon L squared average, or I need to know the variance of epsilon L. I can express it in terms of such an integral where PL of epsilon is the probability density of the L's ordered eigenlevel. It's trivial. But then I want to use a lemma, which tells me that in fact there exists a relation between the probability density of the L's eigenlevel and between the set of probabilities that the interval of the length epsilon contains precisely 0, 1, 2, 3, L minus 1 eigenlevels. So I want to use this relation. I plug it back to here. I plug it back here. I sum up. And what I get is some expression which contains such a nice creature. And such a nice creature which, for example, Nicholas Witte will immediately recognize. It's the generating function for the probabilities that the interval of the length epsilon contains a given number of eigenlevels. Okay, the final formula is, so it's really a very trivial calculation, but that's a nice formula that we get. So the power spectrum at the point omega k is given by such an expression, and the only thing that you have here is a generating function that the interval of the length epsilon contains 0, 1, 2, 3 m eigenlevels. And this one is pretty general, so it doesn't have anything to do with random matrices. It is just general. The only thing that is inside is the stationarity of level spacings. Okay, that's the main result in this part of the talk. And again, I stress that there is no random matrix theory argument involved. So what I want to say is that everything you have seen here in the, so to say, experiment is contained in such a formula. And the only thing is what this generating function is. Of course, it depends on the particular system for which you want to calculate the power spectrum. Another thing that I want to stress is that, look, so the power spectrum is some complicated or not complicated integral of such a generating function. And this generating function contains a contribution of the probabilities that the interval of a given length has 0, 1, 2, 3, m eigenlevels, and this is a drastic difference with what we had for the distribution of level spacing. So in the distribution of level spacing, the only probability of this sort that was important was only E0, the probability of gap formation. Once we are talking about the power spectrum, the entire, oh my God, the entire set of probabilities becomes important. Okay. Now I'm going to apply this formula to the random matrix theory case, which should be relevant for quantum systems with chaotic classical dynamics. And we will see that what arises out of the theory is the Painlevé 6. Painlevé 6, I don't think it works. Painlevé 6 representation of the power spectrum. So in all the works that we have seen before, everything was expressed in terms of the form factor, which is a 2-point characteristics. Now we will see that the right answer contains the contribution of correlation functions of all orders, and these contributions are encoded or taken care of by this 6 Painlevé function. Okay, so how do I proceed? Thanks to the works by Peter Forrester and Nicholas Witzer, it will be very simple. So the first thing I need to do is to define the proper random matrix theory model. Okay. We know from Bohigas that we may use the random matrix theory model. The problem here is that we need to unfold the spectrum of this random matrix model, and this is something which is not easy to do. Another thing, it will not be easy to do if we want to find the exact solution for an eigenvalue sequence of a given length. So still, I do not demand now that the number of eigenlevels will be infinite. So the solutions that I'm going to present will valid for an arbitrary number of eigenlevels in the sequence. So it looks like, at least I think it's for most of the random matrix theory people, it looks like the appropriate ensemble would be circle unitary ensemble, because everyone knows that in the circle unitary ensemble, the mean density is a constant. And this sort of suggests that probably this is the ensemble where unfolding is trivial. Unfortunately, it turns out that the sequence of spacings in the circle unitary ensemble is not stationary. And that was something that we assumed. For example, you wouldn't be able to prove for the circle unitary ensemble such a thing with q equal 1 or 2. You also may do some very simple calculations in Matematica and numerics, and you will see that it doesn't hold. Fortunately, we realized that we need a little bit tune the CUE ensemble in the following way. So we have m eigenvalues on the circle, and we put an extra charge or extra eigenvalue at 0. What it does, it a little bit disturbs the mean density around 0. But what it also does, it induces stationarity in level spacings, and that's the so-called tuned CUE ensemble that we define. So this unity comes from the additional charge or additional eigenvalue placed at 0. For such an ensemble, one can prove the following lemmas. Okay, first, the lemma number 1 is sort of trivial. It just tells you that you have a circle symmetry, and say statistics of theta 1 is more or less the same as the statistics of theta m, etc., etc. What is more interesting is that you can prove such relations, and what is important here, I mean, it's not important for us, but it is very interesting that for a eigenlevel, for the sequence of spacings to be stationary, we need to prove it only for q equal 1 and 2. In the tuned circle ensemble, you may prove it for arbitrary q. Okay, so it contains more than we need. Okay, so with these lemmas, we may claim that that once we have taken the tuned theory ensemble, the sequence of spacings is stationary, and then we may apply just our formula. And that is what I do in the next slide. All right, so what you see here is the formula, the general formula, which we derived previously. The only thing that I need to do is to take care of this generating function of the probabilities that the interval of the length phi contains 0, 1, 2, 3, etc. eigenlevels. And it's easy to calculate. I mean, that's the eigenvalue integral representation of such a thing. Trivial calculation. This eigenvalue integral has many interesting exact representations. For example, it can be written in terms of the six-Painlevé function, or it can be written as a Fredholm determinant, or it can be written as a Topliss determinant, and it is particular tasks that we want to accomplish in order to choose a proper representation. For example, if I want to write just the exact solution for the power spectrum of the sequence with a given number of eigenlevels without demanding that it will be large, thanks to Forrester and Witte, we have such a representation. So the final answer, the exact one for the power spectrum of m eigenlevels, doesn't matter what m is, not necessarily large, is given by such an integral, where phi m, the generating function, can be written in terms of the six-Painlevé function, which satisfies this nonlinear differential equation, and which is subject to the boundary conditions at infinity. And inside these boundary conditions, we have this zeta, and this zeta is 1 minus z, and z is e to the power I omega. So we want to say that this parameter contains the frequency which appears here. So it's non-trivial boundary conditions. And in my view, that's the legitimate exact solution for the problem. Of course, the question is how you use it. Okay? Fortunately, I don't want to use it because this is the starting point for the next step. And the next step would be the large M analysis. Because what I want to do in the very end, I want to let M go to infinity in order to find the parameter-free prediction for the power spectrum. It is this one that is expected to be of relevance for quantum periodic systems, because there we don't have any M. Okay? And that is what I'm going to do. By the way, there are two other representations which are equally good or equally bad, representation in terms of Fredholm determinant. So you can rewrite the, again, I don't see it. You can rewrite this generating function as a Fredholm determinant, where Km here is the scalar kernel for the tuned theory ensemble. It can be written in terms of Jacobi orthogonal polynomials, and these are orthogonal polynomials which are orthogonal on the unit circle with the weight which is 1 minus cosine theta. So this another representation that can be used if necessary. And the third one is the most important for us. It is representation of the generating function in terms of Topliss determinant. So it can be written, again, a matter of simple calculation, a multiple integral of the product of two determinants with some weight function. It can be written as the Topliss determinant whose Fisher-Hartwig symbol has a power law singularity and two jump discontinuities because of the integration domain. And it turns out that the large M analysis of these Topliss determinants was done very carefully in 2015 by the group of Tom Claes. And that is what we are going to use in order to perform the large M analysis. It is important to stress that since this generating function, since this Topliss determinant enters the integral, we are interested in the uniform asymptotics in phi, which is a highly non-trivial issue, and it was studied for a large class of Topliss determinants by Kleist and company, and our Topliss determinant is just a particular case of what they studied. Still, it is not just the trivial rewriting, believe me, because the calculation and estimates of all sort of terms that can be thrown away is some 10 pages, even more, of calculations. Anyway, that's the technical step that one has to do. So we need to analyze this Topliss determinant as m goes to infinity, substitute accurately the asymptotic expansion of that into the integral. We need to look carefully at the terms that can be thrown away. We need to take care of all the terms that need to be kept. The final answer is here we are. Let's take a look. So what I write here is the final answer for the power spectrum in quantum chaotic systems. And this power spectrum and this answer does not contain a single parameter, right? So what we have here, let's see. So the function a of omega, it's just some combination of Barnes G function. B of omega is some other, okay, it's a combination of gamma function, etc. Everything is written here. Sigma, you have double integral, unfortunately, but you do have it. And sigma tau omega k is the fifth Painlevé transcendent, which satisfies this equation at nu equal 1, subject to, oh my goodness, subject to this boundary condition at infinity. So 1, 2, 3, this provides a closed answer for the universal Painlevé 5 law for the power spectrum. Now what I'm going to do is quite a simple thing. So we have an exact solution, if you wish, for the problem of power spectrum. I want to see now, first, what is the relation between our solution and the claims that have been done in the literature in the past 10 years. I also want to do numerics and see if it fits or not, because the calculation, you know, is 10 pages long. And maybe we were wrong. Okay. So first, because of the presence of this, the fifth Painlevé transcendent, this formula for the power spectrum accounts for correlation functions of all orders. I stress it again. There is no second-order correlation functions involved only. Everything is there. The formula is parameter-free. It has nothing in common with the result obtained by the Spanish group in the form factor approximation. This is the entire result that they have, not only, which was claimed to be valid not only for omega k much smaller than 1, but the entire region of omega k from 0 to pi. So as you see, everything you have here is a form factor. Nothing of this sort you see in the exact solution. More than that, this exact solution can be used in order to extract various asymptotics of the power spectrum. For example, it's a pretty easy task to study the small omega k expansion of the exact result, and that is what you get. So you have the leading coordinate singular term, 1 over 4 pi square omega k tilde, and omega k tilde is omega k divided by 2 pi, which coincides with the simple small omega k result by the Spanish group. But all the rest has nothing to do with this formula. Okay? There is no single chance for beta equal 2, for example, to get omega log omega term in the expansion, because k beta of omega k over 2 pi is just a linear function. Okay? So we see that even though the leading Cauchy behavior, the most singular one, is reproduced correctly by this formula, all the rest is missing there. Now let's go to the numerics. The numerics that I show here is the following. So on this axis, I plot the power spectrum minus the most singular term, okay? Because the most singular term is the same in the exact solution and in the form factor approximation. Now, what you see here as blue crosses is the result of calculating the powers. Okay, so so if we would have just 1 over omega k dependence, then this difference will be just this line, right? This one. We are at 0. Everything which differs or deviates from this line is a non-trivial correction to 1 over 2 pi omega k law. Okay? So what we do is the following. So blue crosses are results for the power spectrum calculated for the circle unitary ensemble. For 200 eigenlevels involved into the calculation, and this was average of I think 4 million realizations of CUE. Okay? The red line is our analytic prediction. So we see that it describes pretty well the numerics. The green line is a solution, the full solution based on the form factor approximation, and you see it has nothing to do with numerics. What you see here in the inset is again, so the red line here is the exact solution in a certain region of omegas. The green line is the form factor approximation, and the dotted black line is a small omega k expansion that we derived analytically. So we see that oh my goodness, that in the region of small omega k, there's a beautiful agreement between something goes wrong with the, okay, here we are. And in the region of small omega k's, we see there's a nice agreement between the exact solution and between the asymptotic expansion for omega k much smaller than 1. Again, the form factor theory is far away. Okay. At this plot, we see the power spectrum. Again, so the crosses is a random matrix theory simulation for the entire power spectrum without the most singular term being subtracted. The red line is the theory, the exact theory, and for example, and the 1 over omega k dependence is this line in the inset. So it turns out that the difference between the exact solution and the simple 1 over omega k law, with all the prefactors taken into account, can be as large as 34%. Okay, and in this region of relatively small omegas, the difference is quite small, it's 5%. Okay? Still, it is high, for example, than the accuracy of the, it's worse than the accuracy of the Wigner surmise as compared with the Painlevé solution. Okay? Fine. So the thing that I want to say is the following. So we developed the exact theory for the power spectrum. We compared it with the numerics for the circle unitary ensemble, and it's 3 minutes. Still not enough for us, because I always want to see something. I mean, I want to see the real system. A real system where I see our prediction. That's a good thing to do. Now, we may argue about the philosophical question, what the real system is. But for example, if I take the zeros of Riemann zeta function, for me it is a real system. And what I want to do, I want to take the zeros of the Riemann zeta function, calculate the power spectrum for the Riemann zeta function. It's not a matrix, it's just some mathematical object, and compare it with the prediction of our theory. That's the result. Great. So let's take a look. So what you have here is the plot for the difference between the power spectrum and between its most singular part. The red line is our theoretical prediction. The blue lines fluctuating one is a power spectrum computed for the Riemann zeta functions, for the zeros of the Riemann zeta function, once we have taken 1,000 sequences of zeros. Each sequence is of the length 1,000. So it was an average. Here we had an average of 1,000 realizations. Okay? So we still see, okay, it suggests that perhaps here we have a good agreement with our prediction. Here something else happens. Anyway, we wanted to see more precisely what's going on here. So we obtained 20 billions of zeros from Adlischka. And so far, we managed to use 1 billion of zeros to make the calculation. Here is the result. So now what you see that the fluctuations are completely or quite washed out in the region of large omegas, okay, up to pi here. Here you still see the sort of peaks which have nothing to do with our prediction. Okay? And this is not surprising because it is known, and it can be argued based on the semi-classical theory, that at some omega, the universal prescription, the random matrix theory should break down. It's something which is well known. And if you want to go and describe the behavior of things here for smaller omegas, we need to use the semi-classical approach. That is what we have done. And that is the result. So it's possible to develop the semi-classical theory for the power spectrum for the Riemann zeta function. What you see here in blue peaks are the real peaks which we have obtained from the Adlischka data. What you see here as the dotted lines is the position of the peaks as predicted by the semi-classical theory, and these positions depend, basically numbered by p's, by prime numbers. And you see an excellent agreement. So this formula, simple one, basically reproduces each and every peak here. More than that, we would like to know what happens to the height of each peak. It's a little bit more tricky. So we need to calculate it makes sense to calculate the integral of that just to see the step functions. And again, if we do that and plot here both numerics, I mean, the experiment on the Riemann zeta, and our analytical prediction for such a thing, we again see, you just almost cannot distinguish between the two curves. Conclusions. So we managed to formulate a general framework for the power spectrum of eigenlevel sequences, assuming stationarity of the spacings. We found exact finite M RMT solution in terms of the 6 Painlevé transcendent for a particular class, symmetry class BTVL2, which is the simplest one. We performed the large N analysis of the result based on the works by mathematicians who studied the asymptotics of certain types of topless determinants. And we predicted as a result the parameter-free Painlevé 5 law is a universal one for the power spectrum in quantum chaotic systems with BT=2 symmetry. We found remarkable agreement between our predictions and the CUE numerics and the Riemann zeta function in the later case in the universal domain. The deviations between the exact theory and a simple 1 over omega k law can be as large as 34%. There's a bunch of questions that we still want to address. Thank you.
Are there any questions?
Okay. I have two comments. The first one is for a general class of turbulence determinants that you have, including yours, but also other examples, there is in fact a systematic form factor expansion.
There is or there is not?
There is a form factor expansion.
What is meant by
it's an expansion actually in the generating function parameter. A series expansion in that zeta, and each term of those is a multiple integral.
Is?
So what I'm saying is that you can actually take the exact full result and do an expansion, a form factor expansion, and demonstrate that the previous theory was just a truncation of that.
Okay.
And in fact, so you can actually find what the corrections are specifically. So you can do that for a class of determinants. It's one example where it's explicitly written out is in the Ising model for the diagonal spin correlations. So you have a Toeplitz determinant form for those. And that's been written out to arbitrary order, in a sense. So you can actually go a little bit further than what you've gone and show exactly where it's been approximated in corrections. The other thing is just the minor thing is that there is a quick and easy way to get the large N asymptotics for the P6 tau function. So I can show you a result where you can get the leading order and some other terms as well with a bit more work. It's a straightforward expansion of the elements of the Toeplitz determinant and then making sure that you're collecting them all at the right order to find the leading order form for the tau function.
Yeah, the question is, or the point here is that what we have stands inside the integral, and we need to integrate it over this phi.
Yeah.
And
so
then the uniformity of this expansion is very important.
Yes.
And I don't know.
It's valid.
Okay.
It is uniform, yeah.
Okay.
Yeah. So it's just an alternative way that was
I would appreciate receiving a reference.
And it actually gives you the tau function itself, so you don't have to find the sigma function and then integrate it and exponentiate. There's actually a formula for the tau function itself. So that's an important piece of your integrand and your outer integral.
Thank you.
So,
Eugene, in your last slide, in the list of open problems, you said missing eigenvalue problem. What is this?
It turns out that in recent years, this statistics, which is the power spectrum, was extensively used to extract out of the experiment the parameter, which is the proportion of the missing eigenlevel. So what happens in the experiment is that it is not always that you measure all the peaks or resolve all the peaks that you have. So in any real experiment, you miss some of them. And it turns out that the power spectrum is extremely sensitive to this parameter. What happens is that the same group developed the theory, but which is again based on the form factor approximation, and based on that theory, first they may predict what is the expected influence of this proportion on the power spectrum. Second, they use it in order to deal with experimental data. And here, here's the point we want to enter and say, look, if you have the inaccuracy of 34%, it could happen that it could not happen, I don't know, for 1,000 reasons, but at least theoretically it could happen that you need to improve these procedures that they use, because if you have from the very beginning 34% difference, then it could be that the outcomes that they have for the proportion of missing eigenlevels is just need to be corrected. And that's one of the things that we want to do. And it is pretty straightforward to do in this approach, because the modifications will be very minor.
Okay, but it's not the problem of Riemann zeros functions.
You may do it also with the Riemann zeta function, not a problem, right? You may, again, make a numerical experiment where you just pick with a certain probability each zero and test it there. It's a beautiful playing ground.
Okay, so let's thank the speaker again.
Thank you. And as the last speaker, I also want to thank the organizers. Okay, right. So I want to thank the organizers for this nice conference. And personally, I think that within the random matrix theory community and community of mathematicians around it, with orthogonal polynomials, etc., what is missing is conferences where we have both communities together. And I think that's something which is missing, and it could be very nice if these sort of joint conferences would be held in the future. And for example, in October, we'll have in Israel a large conference which will last for 5 days. And there are also mathematicians and physicists, and everybody is welcome to think about it. Thank you.
The last chairman, I would like also to thank the organizers, Galina, Maria, David, and Jan, for organizing a wonderful meeting in a beautiful surrounding. We have enjoyed staying here and discussing mathematics and visiting Pisa Tower. Nobody destroyed it, fortunately. Okay, thank you very much. Announcements from organizers?
Well, in the name of the organizing committee, I want to thank you all, especially those of you who stayed until the last. Do you want to add something, Professor Chen? Okay, then. Yeah.
Listen, the thing is this, is that the Singapore thing, the Singapore guys said, I need to go and have, in 4th of June, I need to go and have one of these video conferencing, make a 15 minutes presentation for this Random Matrices Eurasia 2020. Now, Random Matrices Eurasia 2019 is kind of too close, right? 2019 is coming very soon. Yeah, well, I don't know. So forget about 2019, let's do 2020 in Singapore. If they have, you see, money is not a problem in Singapore. They have money. That's the thing. Money is not the problem. It depends on what I sell to them, how I sell them. So if I could get an email, a little bit 5 words, or not 5 words, 2 paragraphs each, from each of you, you have my email, what you like to see, what you like to have in the Random Matrices Eurasia 2020, that would be good. I can kind of put it to, huh? A wish list. They pay first class hotel and the return ticket. Yeah, that kind of thing. Okay.
So also I would like to thank all of you for coming here, for giving very interesting talks, and I hope you enjoyed here the conference, and maybe we can see each other again somewhere else. So have a good flight, all of you, and so hope some new collaborations have started and everything is nice here. Okay. I'd like to thank all of you. Thank you.